My name is Josh, and today what we're going to be doing is going through a bit of a head start lecture for our Chemistry 3-4 content. And essentially what's going to happen with this head start lecture is we're going to briefly touch through most of Area Study 1 and a little bit of Area Study 2 of Unit 3. So we're not going to go through the entirety of Chemistry 3-4 today, and I think that's a really, really important point. Now, why is this not letting me put this as a full screen? I'm having bulk technical issues at the moment. I apologize. And I have no idea why. It's really frustrating me. But nonetheless, what we have over here is Slido. So as you can keep seeing, I keep flicking across. This is Slido. Essentially, what's going to happen with Slido is this is where your questions are going to come through. Upvote the questions you want me to answer. I'll go through them. And try not to repeat questions. If the question's already been asked, there's no point repeating it. So just upvote the question, because if that's a question you want to ask, it's already there. Upvote it. I'm going to answer the questions that are most upvoted. Essentially, that's how that is going to work there. Now let me move that one back across. Jeez. Now my Mac is struggling to deal with this. All right, we are here. Now this should be up and running. I'm just going to put that there, just so I know that's running. All right. So welcome everyone. Apologies it's taking a couple of minutes, but these lectures are run by ATAR Notes, and I work for a company called ShootSmart, which is a part of ATAR Notes. ATAR Notes has been around for a very long time. I went to these lectures a very long time ago when I was also a student, and so essentially they're great. They got me through. I remember attending them pretty much every term break before term 1, in between term 1 and 2, etc. And now they're more online, which is more accessible for a lot of people. We do also have some in-person ones coming up, but essentially that's kind of how we've evolved with COVID, and we still offer all the free resources that have always been there. And so some of these, as you can see here, if you go to the ATAR Notes website, you can see the study notes. You can watch recordings of lectures, even old lectures. If you want to get a head start on maybe Unit 4, you can go back and watch the sort of the winter lecture, so the in-between term 2 and 3 lecture from last year, because that's what that would cover. There's lots of videos, lots of different articles and discussions, and then we have some paid resources, which we will discuss as we go through today. And so I work for the ShootSmart part of this, and you'll see a little bit about what that is. So lecture plan for today, as I've already briefly discussed, block 1, fuels and thermochem, and then block 2 is going to be our electrochem, and a few little tips at the end, just because I think it's really important that at the start of the year we kind of go through how to approach things rather than what we're doing. We're also going to have 2 10-minute blocks of questions, and we'll have a bit of a break in the middle. I've said 10 minutes, but it usually is a little bit less than that because we usually run out of time. So there will be a little bit of a break in the middle, and maybe 5, maybe 10, but we will have a break because 2.5 hours is a really long time. But those 10-minute question blocks is where I'm going to answer all your questions. So ask all your questions now. I'll come back and answer them through the Slido. Just a couple of things. Lecture slides should be available. If they're not, they sometimes go up a little bit late. I may have uploaded these slides to my work a little bit late, so they may not be up yet. It is a long slide. It is a long lecture, so please do take breaks, and we will jump in it. So who am I? I didn't put anything in there this year. I was a little bit lazy. So my name's Josh. As I said, I've been working for ShootSmart, which is part of ATAR Notes, for about going on 4 years, nearly 5 years now. So I graduated in 2018, a very long time ago, and I'm currently a medical student. I should be going into my 5th year, but I'm actually doing an honours year this year. So I've done 4 years of medicine, I'm doing an honours year, then next year I'll do my 5th year and I'll finish off. So I didn't think 5 years was enough. I decided to make it 6. And I'm at Monash University. I graduated with a 98 point something. It's a very long time ago, but I had a 44 in chemistry, which scaled up quite nicely because we all know chemistry scales up beautifully, and we love that. And I've been tutoring chemistry ever since. I run a class at Shoot Smart. I've been running a class for all of my 4 years there, and going in now my 5th year, I'm running the Chemistry 3-4 class again. So kind of just what I do. I enjoy chemistry the most. I can tutor maths, but I like chemistry a little bit more. So that's essentially what I do and who I am. And to be honest, that's sort of how I get my credentials to be here. So I think what's really important is there's a couple of things I want to note about, particularly about this year, and then things that won't affect you because they'll be next year. The chemistry study design is changing. However, luckily for you, you are the last year of the old study design. So essentially what is happening is nearly all the subjects at 3-4 level have new study designs this year. And you've probably already witnessed that through maybe some notes or etc. And you've seen, oh, everything's changing. Nothing's super drastic, but what's important about chemistry is 3-4 isn't changing. Why isn't it changing? Because 3-4 chemistry is actually changing a lot. And so what they've said is they've gone, the things that we're adding into 3-4 chemistry next year are so big that we need to add them into 1-2 first, get them sort of established, and then move through. So essentially what's happened is 1-2 chemistry is being completely gutted and completely changed. And the first year of that is this year. So the year 11s will have a completely different 1-2 chemistry to what you did, because their 3-4 chemistry is then going to flow on from that. Whereas your 3-4 chemistry flows on from what 1-2 chemistry was last year. So please don't worry. If you're reading through study designs and you open up the 2023 to 2027 study design, that's actually the wrong one. And you'll note when you get to the 3-4 chemistry part of that, it says, note, this is not to be introduced until 2024. So it's really, really important that you still use the old document, which you can still find on the VCAR website. And the document says, I think it says something along the lines of like 2017 to 2022. But that is your document because you will use that this year. So that's just a really, really important thing. But there are some really important things from 1-2 chemistry that you need to carry on to 3-4. If these are areas you struggled in, I really recommend over the next, 2 weeks before you start back, that you have a little bit of a revision of these, you practice them again, because these are the things that you need to be able to cover. So what you need to know are these things here, and what you sort of are helpful to know are these other things here. Now, every year I say that I'm going to edit this, and I should edit it. I would say this is arguably one of the more important things. I would say, there's a beautiful arrow, as you can see. I would say that needs to go over to there. I would say relative strengths of bonds comes up all the time, especially when we talk about organic molecules or organic chemistry. Organic chemistry is a massive part. It's practically all of Unit 4. I'll be honest with you. Unit 4 has 2 areas of studies. Organic chem, and then this food chem, little tiny one. The food chem is very, very low yield in terms of there's not a lot of exam questions on it. The organic chem can be broken up into 2. The organic chem can be broken up into just pure organic chem and then spectroscopy. However, they are one area of study. It is massive. It takes up most of Unit 4, and it's a massive part of the exams. So I think relative strengths of bonds is really important. Basic hydrocarbon knowledge is also really important. However, it gets retaught, and it's explicitly part of the study design that they start from the start again. So that's why we say it's helpful to know, because you already know it. Therefore, when you retaught, it's kind of revision. But it's also one of those things where it's like, they're going to reteach it from the start. And that's essentially what happens. That's what it kind of is explicitly mentioned in the study design. What you need to know, and what I think is super duper important, as I put my charge from my laptop, is the concept of mole. You need to know how to utilize moles. You need to know how to write and balance moles. You need to know how mole calculations work, and stoichiometry and all of those things. Concentration calculations, all those formulas there, they all have calculations there. You need to know how to use those really well. I would say this one less so. That one doesn't come up very much, but the other 2 super, super important. So Those concepts there, they're very broad concepts, but they are the broad concepts you need to know, you need to understand to apply. And then the other things we've talked about here, redox basics, again, another one of those things they kind of explicitly teach again. Acid, base, and pH. You don't need to know pH calculations. You don't need to know those acid, base, general formulas. What you need to know is titrations. That's about it. Specific heat capacity of water, again, sort of gets retaught, so that's why it's kind of helpful to know, but it's there. And what do you need to know? You need to know all of this. So this is the study design. Notice how this picture says 2021. That's because this screenshot has come from prior to COVID, because this slide has not needed updating. So I've just never bothered updating it, despite the fact I've run this lecture for the last 4 years. This study design was meant to end at 2021. It then got extended to 2022. It's now been extended to 2023. I actually haven't checked, but I'm sure the study design document probably says 2023 on it now. But it does say 2022 as of last year. I'm sure it now says 2023. And that's because they've pushed everything back with COVID, but essentially you are still on this study design, and it's really important that you recognize that you're on this one. And yes, please read it. So what do you need to know in terms of what are the 6 main topics? This is what the 6 main topics are. So we have Unit 1, Unit 3, we have 3 area studies. We have 2 area studies, but we break them up into 3. We have fuels and electrochem. These 2 are sort of a part of one, but we sort of break them up. And then you have rates and equilibrii and a little bit more electrochem. Really interesting. They kind of also sort of break these 2 up. That's sort of broken down in the middle. But essentially how we topic it is we topic it as fuels, electrochem, rates and equilibrii. So 3 topics. Unit 4, experimental design. You've been through experimental design 1,000 times. I'm sure you'll all be all over it. Organic chem, food chem. And then what we've done is we've got the study design and we've broken it down into what is its basic parts. This is the study design as summarized as can be. I don't want you to use this as your study design. I'm happy for you to use it for now and just sort of look through and say, oh, these are the things I'm going to be learning. But when you're reviewing and you're revising at the end of the year, you're going to use your proper study design. Why? Because this doesn't go into super detail like the study design does, and you need to go into super detail at that time of the year. But this is just as summarized as we could get it. So essentially, these are the topics that you have within the topic. So you have fuels, electrochem, and equilibrii, and then the little topics within it. Experimental design, there's not really any subtopics because it's just experimental things. And then organic chem, as you can see here, we split into 3 here, but essentially these are 1. This here, analysis, is as big as all these points here. But those analysis points, those 2 analysis points, are as big as that whole organic chem part there. Analysis is really, really large. So is just the rest of organic chem. And then we have food chem. This stuff is fairly straightforward, and most schools do this in about 2 weeks or 3 weeks. Food chem is done extremely quickly. It's not really one that people dawdle on. They sort of just do it very quickly and get it done with, because usually in the exam there's not many marks on it. And it's why pretty much all of this is getting culled for next year's study design. But for you, it's still there. And to be honest, it's usually fairly easy marks because food chem isn't really all that difficult either. It's not like analysis, which can be really difficult, or some organic chem can be extremely difficult. Food chem is fairly straightforward. So we're going to move into topic 1, thermochem. Now, just before we start, there's always a question, and it's always in there somewhere. They always say, oh, like, how should I use today? How should I study today? Should I take lots of notes? What should I do? I think the best utilization for today is if you haven't seen this stuff before. So some of the fuel stuff I'm sure you will have because you will have done a bit of Headstart. Everyone does. But if you have only been through a few things, you're going to start to see some stuff that you haven't been over before. I think the best utilization for today is to sort of sit back, maybe have a notepad there, and just jot down big, broad points. I don't want you to go through, like example for this slide, and write down all these dot points. Why? 1, because you're going to get these slides. There's no point writing this all down. 2, because you're not going to go back to these notes. You're going to go back to notes that are big, broad sort of concepts saying, I need to revise this. I need to look into this. I need to go through different types of fuels. That's going to get you to come back to it, because you're going to come back and go, all right, I now need to go and do that. So then you're going to go ahead and do that. So for today, what I say is sort of sit back, just sort of take it in, and just jot down some points that you think are important, or some points that you want to come back to, sort of like little tick boxes to say, how I want to come back and look at that. That's sort of the best way to go about the content you'll see today. So we're going to start off with fuels. Essentially, fuels can be broken down into two things: fuel choices and obtaining energy from fuel. So what is a fuel? A fuel is a substance that can be reacted with other substances, e.g. oxygen, leading to the release of energy that can be harnessed for a specific purpose. What's really important about this is that this is an explicit definition that you need to know. What's going to be really annoying about this first part of fuels? It's a lot of rote learning. What I mean by rote learning, for those who don't know what that's what it means you just need to memorize things. It starts to feel like, I always pick on the other science subjects, and I would say that it starts to feel a lot like psychology, because it's just memorizing. There's the first part of fuels, there's not a lot of maths, and there's not a lot of sort of explicit thinking or trying to problem solve. It's really just, what can I remember? Put it back down on the page. So the wording for the definition here is important, because fuels, you don't want to say fuels can be combusted. You need to say the fuels can be reacted with other substances. So just a really important wording there. As I said, it's explicitly stated in the study design. And then what is renewable versus non-renewable? Another set of definitions which isn't explicitly asked for, but has been asked before in an exam. So what is renewable? Renewable is a resource that can be replenished by natural processes in a relatively short period of time. Another way of wording this in a wording that I tended to use was, it's a natural process which can renew the fuel quicker than we utilize the fuel. Or it's quicker in producing than what we use it. So think about if you're doing something and you're utilizing something, but it's being produced quicker than you can utilize it, thus you're always going to get more. Whereas non-renewable is the opposite. As you use it, it cannot be replenished in that period of time. So fossil fuels, for example, they take thousands of years to form. We can use lots of fossil fuels in a day, but we can't produce lots of fossil fuels in a day. It takes thousands of years to form. So that's the sort of idea behind renewable and non-renewable. And then we have fossil fuels versus biofuels. So essentially, this is how you sort of break down your non-renewable. So fossil fuels derived from living matter, underground for millions of years. Biofuels derived from plant matter and can be produced at the same rate we consume it. So what are the ones you need to know? These are the ones that you need to know. So you need to know coal seam gas, crude oil, LPG. Crude oil is the main one you need to know. You'll know that as sort of crude oil, petroleum, petrodiesel. Petrodiesel falls under crude oil. Biogas, bioethanol, biodiesel. They're the three mains you need to know for biofuels. Really important. This is the one you need to know the most about. So this is the one you need to know the most about. This is the one you need to know the most about. They always will ask you to compare biodiesel with petrodiesel. They're the two they always ask you to compare. That's just what happens. And these are the things they like to ask you to compare: energy content, renewability, environmental impacts. We'll go through them. So we're just going to go through each of these quickly now. What's really important about these slides is I've sort of been creating these slides over the last 4 years, so there's way too much information in them, etc., and all that sort of stuff. So essentially what I'm trying to say to you is that I will highlight what is most important here. So key point, it's produced by anaerobic bacteria that decomposes organic waste. So essentially what happens is you put organic waste, whatever that is, into this sort of big dome. As you can see there, it's just like a big sort of composter in a sense. And essentially there's lots of bacteria in there. Bacteria deal with it and they produce biogas. They produce a methane type gas. Now what's really important about this is that it's mostly methane, but it's not pure methane. This is the fuel component. This is the non-fuel component. Don't worry about these values. I'm just trying to explain that essentially there's a lot of methane, but there's not 100% methane. And then there's also trace amounts of other products. This was asked for once about 7-8 years ago, and it has been asked for again, so I wouldn't worry too much about it. And because it contains less methane than fossil fuel gases, so coal seam gas has 96%, methane, it releases less energy because that's where the energy comes from. So being less percentage, it's going to be less energy released. And then this is the combustion equation here. Bioethanol, so this is produced from the fermentation of glucose by yeast. So essentially glucose gets fermented and it produces ethanol and CO2. And you'll see it a lot in those sort of E10 fuels. So, you know, if you drive past, I think it's United. United always tend to have it. They always have E10 at the top, and you always think, oh, their petrol's really cheap, but it's not, because it's their E10 that they're advertising as their main petrol. And E10's always cheaper because bioethanol is pretty easy to produce. It just doesn't have a lot of energy. So E10 fuel is not as strong or as sort of fuel efficient as normal fuel. That's why it's a little bit cheaper, because you need more. You need to fill up more often because you don't get as much out of it. And then biodiesel. This is the most important one. It's produced by using plant oils or animal fats in a transesterification reaction. So you get triglyceride plus methanol goes to glycerol plus biodiesel. And essentially, this is a really ugly and big reaction right here. Don't worry about this right now. You will learn this when you get more into food chem. It's the one important part of food chem that you'll learn. So don't worry too much about this right now. But it's nice to sort of just visualize what's going on. But this is most important when we get to food chem. So what's really important to note at the biodiesel is the name. So we call it a fatty acid methyl ester, or a FAME, but you're always going to call it a fatty acid methyl ester. And it's one of the most confusing parts of the course because it mixes knowledges from multiple area studies, as you can see there. So don't stress too much. We're going to go through this in organic chem and then mainly through food chem. So it's mainly going to be uniform. So some disadvantages and advantages. Now, why I've got these slides in here is because I think it's a really good way to revise this content. So this content is really difficult to revise. That is the reality of it. Because it's rote learning, it's memorization, it's things like flashcards, writing things down. It's the only way to learn. And like flashcards are pretty useless these days. Like, to be honest, the way VCAR exams are being written and the way that they're being produced, flashcards are not really that useful. Why do I say that? It's because VCAR's writing exams in the way that if you memorize something, you're going to get 1 of the 4 marks. They want you to be able to sort of problem solve and work your way through an example. Chem exams are really, really like that. However, this topic here, less so. So this topic here is one of those ones where you just kind of have to memorize. And so doing these tables like this, so doing a table where you say, all right, what is the advantage and disadvantage of a fossil fuel versus a biofuel? And you make a table, you say, all right, my advantages are high energy content, easy to release energy, relatively easy to obtain, extensive existing infrastructure. So one of the other things about that is common sense things. Think of this as a common sense example. This isn't something that's going to be explicitly taught to you, but it's common sense. We've been using fossil fuels for the last 100 years. So there's lots of remaining infrastructure. We have coal mines everywhere. Like, those things have been built for many, many years. We've sort of refined that science there to a point where we're very good at obtaining fossil fuels. Yes, it's not good for the environment, but it's something we've been doing forever. So we already have it there. Whereas if you think about biofuel, probably the last 20 years or the last 15 years is we've really started to push the environmentally friendly fuels, and we've really tried to start dephasing or phasing out our sort of coal mines and our crude oil and all of that stuff. And there's pushback everywhere, but eventually it will happen. But one of the things that slows that down is that we don't have the infrastructure in place. We don't have the things built to produce biofuels. So as you can see there, it's a massive advantage for fossil fuels. Disadvantages: non-renewable, emits large amounts of CO2, so it's a really bad greenhouse gas, and lots of other things there. So again, more common sense things. Extremely damaging to the environment. So as you can see there, it doesn't really look all that great. Biofuels, advantages: renewable, relatively carbon neutral. Now we'll talk about this in a second, so don't worry about that terminology. Burns more cleanly, easy to source materials, etc. Disadvantages: lower energy content, so thus you're going to need more biofuel to get the same amount of energy out. can be complicated and costly to produce, can require large amounts of water to grow crops, fertile land, etc. So, what does it mean by carbon neutral? So, what we say by carbon neutral is that when a plant is growing, it absorbs carbon via carbon dioxide. So it absorbs that, and then essentially what happens is when we take that plant and we produce the biofuel, we produce a little bit of CO2. So we sort of say that it's offset. The CO2 that was absorbed by that plant, some of it is being re-released, but that's okay because that plant already absorbed it. So we think of that as a sort of offsetting. We then transport the biofuel. Again, releases a little bit of CO2. Again, we like to think of that as offsetting. So if this was 100%, we like to say this might have been like 30%, this might have been like another 30%, and then we say the biofuel is used, and then we say the rest of the CO2 is reproduced. So we say maybe like 40%. Might be a little bit more, might be a little bit less. As long as it's around that 100% coming in and 100% going out, as long as it's around that, could be 95 going out, could be 105 going out, doesn't really matter if it's a little bit more, a little bit less. But as long as it's very close to each other, we call that carbon neutral. So what we say is that it's the carbon absorbed, or the carbon dioxide absorbed, versus the carbon dioxide released. So it's complicated, but you just need to know sort of how to define it in that sense there. Now, biodiesel versus petrodiesel. So this is the one that VCAR specifically wants you to be able to discuss. So we're going to talk about a couple of aspects here. So the most important thing that I think we should discuss here is sort of the shape. And yes, this is a little bit of organic chem, but organic chem is everywhere. As you can see here, they look identical other than this here. They have an ester bond. That is the only thing that changes them between the two. Biodiesel has an ester, petrodiesel does not. This means that this molecule here is therefore polar. It also means that this molecule here has a much sort of higher boiling point, and it therefore has a higher liquid point or a higher solid point. You've got to remember that this polar aspect changes everything. And this is where I said those intra versus intermolecular bonds, that's where this is really important. What is this going to have? It's going to have hydrogen bonds, dipole-dipole bonds. It's going to have all those things. Whereas petrodiesel isn't really going to have dispersion forces. It's a non-polar molecule. The other thing about petrodiesel is it produces lots of particulates and other toxins. This is sort of beyond the scope of VCAR, but essentially like petrodiesel sometimes has little extra bits here and there that are quite toxic. It's just a part of what it is. So therefore we say that it's quite dangerous. Now, we discussed some other things here. It says strong dipole-dipole bonds making it more viscous. So what is viscous? Viscosity. Viscosity is a word that means thickness. So I always think of viscosity as water versus honey. So you think about water versus honey, you put them both in a cup. If I pour water out of a cup, it's just going to pour. So it's going to get everything wet. I pour honey out of a cup, what's going to happen? It's probably going to take a good 20 seconds to actually leave the cup. It's going to be really cluggy and thick, and it's going to take a while to get out of there. That's the difference. I like to think of that as a difference of viscosity. This is less viscous, the water. It doesn't have a lot of viscosity because it's very fluid. It's a liquid. It moves very freely. The honey is extremely viscous. Why? Because it's thick, it's cluggy, it clogs things up. And that's what we like to think with biodiesel versus petrodiesel. Biodiesel is more like the honey. It's thicker. It is more of like a big cluggy thing. And it can sometimes, when cooled down, block things up because it becomes so much like a jelly. Whereas petrodiesel, because of its non-polar and its weaker dispersion forces, is more like a fluid. It's like a water. It just flows. So if you think about using these in, like, let's just say the Antarctic, you take a car to the Antarctic, a biodiesel is going to clog up the fuel lines because you're going to try and use it and it's just going to clog things up. Whereas petrodiesel, on the other hand, is not going to clog anything up because it's extremely like a liquid. So it's just going to flow. So that's one of the big things we like to talk about in terms of biodiesel versus petrodiesel. Now, the other thing here as well that I think is a really really important slide here is how we compare. So VCAR loves to ask, let's compare. And it's actually one of the things that they're starting to phase out. So they're going to phase this out with the next study design. However, they say they're phasing it out every year, and it's always every year in the exam. You can go back to last year, I'm pretty sure there's a question asking this. So how do we compare? So as you can see here, this is an example VCAR question. With reference to chemical structure, we've just sort of made it a little more summarized. But this was based off a VCAR question. With reference to chemical structure, compare the suitability of biodiesel and petrodiesel as fuels to power vehicles in cold environments. As you can see here, there's no comparison when we say petrodiesel only experiences weak dispersion forces, thus it has a lower cloud point, making it more suitable to use at low temperatures. Now, don't worry about that point, we'll discuss that in a little bit. Essentially what we're saying here is there's no comparison there. As you can see there, it just says petrodiesel is weak, or petrodiesel is weaker, but it doesn't compare to what are we comparing it to. VCAR examiners, when they read a question, or when they read an answer, they don't read the question. They read your answer. They kind of want you to sort of explain what you're explaining. They want you to sort of say what the question was within your answer without saying, all right, the question was this and my answer is this. You don't want to say that. You want to give a bit of summary. So as you can see here, it says, while biodiesel experiences dipole-dipole attractions, petrodiesel only experiences weaker dispersion forces. Thus, petrodiesel has a lower cloud point than biodiesel, making it more suitable for fuels at low temperatures. This is telling me what the question was. The question was, which is more suitable at low temperatures? That is what this last sentence is telling me. It's summarizing things. And what's really important is we mentioned both. We mentioned the biodiesel, we mentioned the petrodiesel, we mentioned the biodiesel again. We continue to mention these things. Like, you need to mention both explicitly and talk about both explicitly when you do a comparison question. So this is a really important slide. I think if you take anything out of today, this is the slide you need to take out of today. So now we're moving more into the fun side of things. This is more of the maths and more of the actual sort of chemistry. So combustion reactions. So combustion reactions are essentially under this general formula. You put a hydrocarbon in, or your fuel, with oxygen, so you just environment. Carbon dioxide plus water comes out. So both of these are fossil fuels. That's why when we burn fuels, we release fossil fuels, or greenhouse gases. No, not fossil fuels, sorry, we release greenhouse gases. I always get those two words mixed up. We release greenhouse gases, apology. So as you can see here, this is a combustion reaction for ethanol. So we've got ethanol here, could be bioethanol. We put the bioethanol in, we have oxygen in there, and then out comes CO2 and H2O. Now, this is in a liquid form. If this is in a gaseous form, this is a greenhouse gas because water vapor is a greenhouse gas. In a liquid form, it's not really. But if it becomes a gas, then we say it is. CO2 definitely is. So that's where we get sort of our greenhouse gas emissions from this. So really important. We balanced everything out here. I'm sure you all know how to balance, but just one of those things. So, practice question. Let's write out the equation for the incomplete combustion of heptane. So, the answer was there. I always forget that I've put the answers in there, and I've put them in there as a transition. So, I think what's really important here is incomplete. So, what I'm trying to teach you here is essentially what is the difference between complete and incomplete. Incomplete occurs when there is not enough oxygen present. So let's just say we're combusting fuel in an airtight fuel tank. But when we have that airtight fuel tank, there's a little bit of oxygen in there, but there's not enough to combust it all. So what happens is, a little bit of chemistry happens, and the fuel goes, all right, well, if we can't combust us all, we may as well combust as much as we can and produce the byproducts that allow us to combust as much as we can. So we put down heptane. Heptane is 7. So that'll be 16, I believe. No, that's on a C. Why don't we put a C there? Apologies. 7H16. And this will probably be in an aqueous form. And then we have oxygen. So that's what we have present. Now, we don't have enough oxygen present, which is the issue. So what are we going to produce? Well, we're going to produce this. We're going to produce carbon monoxide. So if you've heard of carbon monoxide poisoning, the cause of carbon monoxide poisoning, or the production of carbon monoxide, is not enough oxygen being present. Exactly the same thing here. Then we're also still going to get H2O. So essentially in this one here, instead of producing carbon dioxide, we get carbon monoxide. So now we need to go and balance this. If I want to balance this, I'm going to balance my carbons first. So I'm going to put 7 here. Then I want to balance my hydrogens. If I want to balance my hydrogens, I want 8 here. So I've got 7, I've got 8. That's going to be an uneven number, so therefore I'm going to have to then double it. So I would go 2, I would go 14, I would go 16, and then I would have 14 here, I would have 16 here, I'd have 30, that means that needs to be 15. And that one there, they haven't actually given me a balanced. Oh, incomplete. There you go. So, as you can see there, this is the incomplete, which matches up mine, even though you can barely see it there. The only thing they haven't done is they haven't doubled the equation. They've left this as a fraction. Now, I personally always double mine, but it's not necessary. Some teachers will tell you it is. If I was a teacher, would tell you it is. I think leaving it as a fraction is really poor chemistry. We don't get half molecules. So always double. In my mind, I will say always double, but a lot of people will tell you not to worry about it. So again, preference of what your teacher wants, something that you should ask them. But in a VCAR exam, either one is accepted, even though it's poor chemistry. This at university level wouldn't be accepted because you don't get half a molecule. That's reality. So at VCAR level, either is accepted, but I would always double it. I remember I did this ages ago, and I was like, I should change that, and then I never have. Now, thermochemical equations. So, as you can see here, we have the exact same combustion equation, but we have added energy to the end. Now, what that means is that all of these combustion reactions release energy, which is the whole point of it. So we put a fuel in a car because we want the energy, we want the wheels to spin. This is what is happening. We combust the fuel and we get energy out. So these are known as exothermic reactions, and they release energy. However, we do also have things called endothermic reactions. These absorb energy. Fuels don't ever do this. Fuels are always an exothermic reaction, and we'll discuss these in a little bit. But exothermic fuel. Fuel is exo because it releases energy. So as you can see there, all combustion reactions are exothermic. So let's say we combust two different fuels, methane and ethane. So I have the two there. Again, I have a fraction there. Sure, these reactions tell us that when we combust both methane and ethane, energy is released, but they don't tell us how much energy is released. So we need to get the exact values. Now, where do we get these from? We get these from the data booklet, and we call these enthalpy. So enthalpy is H, and that equals energy. So enthalpy is represented by the letter H, and essentially what we say is that when we have high energy, we have a high enthalpy. On the other hand, we have a low enthalpy, and essentially we would represent this one as a H. So it's stored within the bonds, etc. Yeah. You can put the double H there. Don't worry, we'll do that in a little bit. As you can see here, what we've got is an exothermic equation. Now, why is this exothermic? Because, as you can see here, we started out with our reactants. So these are our reactants. So these are what we're starting with. We start with methane, we start with oxygen. We combust them. The combusting is happening here. We then have our products. Our products have a lot less energy. So they have a lot less energy than what our reactants have. So all of this energy in the middle is referred to as delta H. And why do we call it delta H? Because delta, which is this, means change in. So change in enthalpy. We had this much energy to start off with, we had this much at the end. This difference is the change in enthalpy. It's also the energy released. So that is the energy released out. So as you can see here, when it's exothermic, the reactant is always greater than the product because we need to have energy released out. So because the products are less here, energy has to have gone somewhere. And the delta H is the products take the reactants. So it's kind of like the opposite way. What does that tell you? It tells you that the delta H is going to be a negative value. The delta H will be a negative value for exothermic reactions. As you can see here, we have methane, we have O2, it goes to CO2, 2H2O, and the delta H must have been negative 890 kilojoules per mole. So what that's saying is that 890 kilojoules were lost here if 1 mole of methane was combusted. So 890 kilojoules per mole is the enthalpy, but the change is negative because you're losing it. It doesn't mean that the energy is a negative energy. You can't have a negative energy. There's no such thing. What we're saying is that we had energy removed. Energy went elsewhere. And that's essentially what happened here. Endothermic, on the other hand, is the opposite. So what we've got here is, well, what reaction is this? Have a quick think. What do you think this is? It's photosynthesis. So we're producing glucose and O2 from CO2 and water. So it's literally the exact opposite of like a cellular respiration equation. That's because it is the opposite. It's the plant, and the plant uses the water and the CO2, and it produces glucose. But essentially, as you can see here, this is a very energy, this molecule here has lots of energy. So given that, it's going to be really high up here, but neither of these molecules have that much energy, so they're going to be pretty low. So therefore, the delta H is the opposite. It's going up. Therefore, by going up, we're going to say this is positive because energy had to be absorbed in. It's taken energy from elsewhere and absorbed it in. Therefore, we've added energy, so it's a positive, and our delta H is always going to be greater than 1. It consumes it, it brings it in, therefore the energy within the system is now greater, so we say that it's a positive value. So delta H here will always be positive for endothermic reactions. So for combustion, always going to be negative. So enthalpy is measured in kilojoules per mole. And why is that? Essentially, what we're saying is that we've talked about mole 1,000 times. I don't need to go through moles too much. But essentially, what we're saying is that for every mole, we produce this much energy. However, as you can see here, we had 2 mole at the front. So, as much as this is still per mole, this is how much was produced from the 2 moles at the front. So if this had had a 1 out the front, or like nothing out the front, this would have been half of that. That's just because we're representing what was shown in this equation. And what was shown in this equation was there was 2 here. So we make up thermochemical equations in 2 parts. What's really important is you only ever have to write a thermochemical equation down if you are specifically asked for a thermochemical equation. If they ask for just a chemical equation of a combustion reaction, do not give the delta H. Why is that? I don't want it. They're asking for a chemical reaction. They're not asking for the thermochemical aspect. They're just asking for the chemical aspect. And that's really, really important. So this part here goes with this, and it only goes there if it's asked for a thermochemical equation. So the other thing, thermochemical equations can be manipulated. So if we double the coefficients, we double the delta H. If we, as you can see there, so if we started off with 2 here, we went to 4, we doubled it. If we reverse the equation, we then have a negative delta H. So as you can see here, we had the equation of photosynthesis, we flipped it to make it cellular respiration, we now get a negative. Now, if it had been this one that had been flipped up here, this would have become positive. And then if you add 2 equations, you just add their delta H's. So this has happened in a VCAR exam before. They've asked you to do this. So that's why it's something you sort of need to know how to do. So if you add 2 equations, you add them together. Now, what I mean by that is if I'm adding them together, if they're 2 negative values, I add 2 negative values to each other. It's just going to be an even smaller negative value, essentially. A bigger number, but it's going to be more negative. if you add a positive and a negative one, you just add it like a positive and negative. So don't try and manipulate your negatives and your positives. Just do it as they ask you to do it. Now, key point, don't forget the delta H sign. That's wrong. That's right, etc. So I think this is a really good practice question. I think everyone should have a go at this one quickly. So what you have here is you have enthalpy changes in the formation of ozone, and they ask you from these three equations to get to this equation here, and what they are asking for is the delta H of this final reaction. So this is a 5-mark question. It really isn't going to take you as long as a 5-mark question. It came out of one of my 8 notes ones, so it's one of our more difficult ones, but I think it's actually very reasonable at this time. So I want everyone to take sort of maybe 1 or 2 minutes, maybe 3, and have a go at this. So on your notebook, have a go at this question here. Try and get to the correct value. So essentially what you're doing is you're using these equations to get to this equation, and then what you're going to do is get your delta H. So have a go at this. All right, so let's have a look at this one here. I think I've given you enough time. So essentially, if we look at this here, what have we got? We've got an equation that starts out, oh, I didn't mean to do that. Starts out with N2O4. So we have N2O4. We finish with nitrous oxide, and we have O3, which is ozone, as our last. So what I like to think about is I like to sort of label out my equations as my starting point. So I'm just going to get a different color. I'm going to get rid of this, and I'm going to get a different color. So we have equation 1. Now what needs to happen to equation 1? I have this as the only thing that sort of matches up. Neither of these are in my other equation. So what needs to happen is this needs to get onto that side. So I need to swap this one. So I'm then going to rewrite it out. I'm going to say I would do this down here in my sort of my working out, because you want that to be part of your working out. But essentially there are some answers already written out, so that's why I'm not putting it down there. But I would swap it out, and I'd get N2O for gas goes to da 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 da, and I'd get a delta H is equal to negative 11.1. Now the next one, I don't want to flip it because it's already on this side, but I'm pretty happy with it for now. I'm probably going to have to change up the values of it, but I'm happy with it for now. I'm not going to go ahead and do anything to it yet. And then with this one here, I want to get my O3 on this end. Again, I'm happy with it for now. I may have to multiply it or divide it, but for now, 2 and 3, I'm not going to do anything to. Then what I would do from there is I'd add 1 to 2, and then I'd add the product of that to 3. And you're going to do some manipulating with the numbers, as we will show in the answers here. So as you can see, we've flipped that, and we've got our answer. This one here, we've halved. So we've halved it because we want to get one of these N2Os. Next one, again, we halved it again because we only want one of these O3s. So essentially, we add these first two together, they cancel out. This one's actually gone and added them all together at once. And as you can see there, when you add them all together at once, you end up with this as your final maths equation, and you end up with your answer of 213 kilojoules per mole. So I would have personally gone through and added them 1 and 2, and then the product of 1 and 2 to 2 and 3. However, in this case here, they haven't, because they've just gone through and done it all at once, which you're welcome to do as well. You'll still get your full marks for that. Most important thing here is understanding that this, and this needed to be in those forms, and they needed to be by themselves. They need to be on the right side, or the correct side, the right or left, whichever one is the correct side. And that's how you go about that question there. So there were the answers there, and very nice. So heat of combustion. So when we discuss heat of combustion, what I said before is that we're going to go to our data booklet. As you can see here, your data booklet, which is going to be your best friend, by the way, has the heat of combustions and the molar heat of combustion, so kilojoules per mole and kilojoules per gram. You're always going to use kilojoules per mole unless they ask for you to use this. It's just there in case they ask you to, but you're always going to use this one in case they ask for this one. And the molar heat of combustion, as you can see, is all here. It even gives you the state that it will be in. So depending on what it is, you'll find what state it is in. And you can see there your value. So you may get asked to write a thermochemical equation for ethane, but you're not given the molar heat of combustion. And you'll be like, well, what do I write down as my delta H? I'm confused. Well, you go to your data booklet and you'll find it's here. So sort of the next part here is the universal gas law. So I'm not sure if you will have seen this before because it's been explicitly added to the 1-2 study design, but I don't think it was beforehand. So some of you may have seen it, but some of you may not. Essentially what I refer to this as is the Pivot reaction, and the Pivot reaction is PV equals nRT. Now, the most important thing today is to know what the units are. So pressure is in kilopascals, volume is in liters, N is in moles, R is a constant. Now, 8.31 is sufficient. You don't need to put the 4. If the question explicitly asks you to go to 3 decimal places, you'll use the 4. However, 8.31 is sufficient. You can just use 8.31. Temperature, kelvins. Now, quick point on kelvins. Kelvins is degrees Celsius plus 273. Now, why is that? Someone will say to me, why would I bother with degrees Celsius plus 273? Why can't I just use degrees Celsius? Degrees Celsius is amazing. Degrees Celsius, so much better than Fahrenheit, first of all. At 0, what happens? Water freezes. At 100, what happens? Water boils. It just makes sense. Degrees Celsius is a really, really logical thing. And why is that? Because it was created a lot later on. Degrees Celsius was only really something that was created, I think, through the 18 or 1900s. Kelvins was what we used sort of at the same time, as created around the same time, but it was also created just a little bit earlier. We used it a little bit earlier, and why is that? Because we discovered that if we go as cold as possible, as cold as we possibly can, negative 273 degrees Celsius is the lowest temperature you can possibly get something to. You cannot go any lower than that. I'm sure there are some chemical explanations for this. I don't know them, to be honest with you. I don't do chemistry at university level, so I don't know the answer to why is 273 the lowest value you can get to. I'm sure there is some explanation. If you want to know, go and search up on the internet, you're welcome to. But negative 273 is the lowest possible temperature we can get to. So kelvins has 0 as the lowest possible temperature we can get to. It doesn't have negatives. There's no negative kelvins. You only get to 0. And then from there you add on. So that's why kelvins is the thing. It's used lots in chemistry because in chemistry we work at really low temperatures. So it's better to work at 100 Kelvin than negative 173 degrees. So make sure you use the correct units. I put a practice question in here. We're not going to go through that because we're sort of running out of time. But this is a really good sort of practice question for this topic in terms of that it goes through each of the different points of this equation. Now, do I talk about, just quickly, no I don't. One other point with this is we have this equation that looks like this. V equals N times V M, I think it is, or Vn. It's Vm or Vn, one of the two. I've forgotten what it is, I apologize. This equation here is a derivative of this equation here. Now I'm going to get rid of my little scribbles. Now, what do I mean by that is, I'm sure you've all heard of, and if you haven't, that's okay, SLC conditions. SLC. Now, SLC refers to standard laboratory conditions. Standard laboratory conditions are 25 degrees Celsius or 298 Kelvin, 1 molar concentration, and 100 kilopascals of pressure. What that means is if we're doing an experiment and we want to compare things, and I'm sure you all know your sort of constant variables, your constant variables need to be things you're not manipulating, need to stay the same. When we're doing experiments, we like to have things at SLC because SLC just makes sense. If you have things at SLC, you just are always comparing with other things at SLC. Those things are not going to change the results of your experiment. So, if we look at this, if I'm doing experiments at SLC, I did that. Apologies, everyone. Bring that back. Your 298 Kelvin, should be capital K, I think. Capital K? Yeah, it's capital K, yeah. Your 298 Kelvin goes in as your temperature. So we now have 298 here. Your 1 molar concentration isn't really in this, so don't worry. Your 8.31 is always going to be the same because it's a constant. It's always going to be 8.31. Your pressure is going to be 100. So if I then look at this, I only have 2 values left. I essentially have 100V equals, I'll do it very quickly on my phone, sorry, 8.31 times by 298. Essentially we have 2,476.38 N. That's what you have. You have an equation left. Now, if you continue to do this, what you end up with is this equation here. V equals N times 24.8. So, if you are given a question and they give you 25 degrees, they give you 100 kilopascals, they give you 8.31, and then they give you a moles or a volume, either one. They'll say maybe the volume is 2 liters, and they want you to find the moles. You could go ahead and plug it into this big equation here. Or you could go, oh, I already know that I'm at SLC, so all I need to do is go 2 liters equals N times 24.8. Or the other way around. If I'm told I have 2 moles, I go volume equals, or we'll say 3 moles, not to confuse everyone, 3 moles times by 24.8. Find my volume. So this is another equation that is really, really useful, and it's in the VCAR data booklet. It's in the VCAR study design. However, VCAR will ask questions about this, and the one resounding comment they will make in their examiner's reports is that most students will still use this big long equation rather than going ahead and saying, hey, this is at SLC. I can just use this quick one here, which is what you should be doing. So, really important, know this equation. It's at SLC conditions, which are standard laboratory conditions. And essentially, you do a lot of this, a lot of universal gas equation in terms of fuels, because as we go back just very quickly, notice how a lot of these fuels are in gas state. So when these fuels are in gas state, if you think about your thermochemical equation, you have your hydro, or your fuel, and in this case, it's in a gas. You have your O2, which is also a gas. You have your CO2, which is also a gas. And then you have water. Now, what's really interesting about water is it's most of the time it's a liquid. However, in some cases, it can be a gas. And VCAR will sometimes just give you a combustion reaction where everything is a gas. Therefore, as you can see, they also mention SLC here. Therefore, these questions here where they give you everything as a gas, they'll go ahead and they'll be like, everything is a gas, and you go through the question. You then get to here and you need to start utilizing this equation because they're going to ask maths questions that require this equation or require this one down here, which is technically this one here. That VM is 24.8, by the way. That's what we refer to that as. So that's the universal gas equation. Really, really important. The second most important thing, so we had the comparison question. That's the one thing I want you to take out of it. If there was two things you're taking out of it, take out the units. Know what the units are. Know kilopascals, liters, moles, kelvins, and 8.31 is your universal gas equation constant. However, this is in your data booklet, so you don't need to worry too much about that, but you will know it by the end of the year. You'll do so many questions on this. But you need to have everything as kilopascals. You need to convert it to kilopascals if it's not, and there are conversions in your data booklet. You need to have everything as liters. So if it's mils, it needs to go to liters. You need to have everything as moles. If it's a mass, you then need to convert it to a moles. If it's temperature and it's degrees Celsius, you need to convert it to a kelvins. And what do you think VCAR does? VCAR loves to give you everything in different units because they want to trick you. They will do it. They always give it in atmospheres instead of kilopascals, or they always give it in mass instead of moles, or they always give it in degrees Celsius instead of kelvins. It's ridiculous. People get really frustrated about it. It just is what it is. VCAR loves to do it. But that's essentially what it is. So there's a question there if you want to go through it. The answers are also on the next, I think it's the next slide. I hope they're not on the same slide. If they are on the same slide, try and take full screenshots and do them before you go for the answers. But essentially that's block one. That's what we went through. That's pretty much most of thermochemistry. There's the Q equals MC delta T with the specific heat capacity. That's really the only other thing that's a part of this. But that's really the biggest that's a big summary of thermochemistry and really a big summary of all of our fuel that are area study 1. So that's area study 1. We're going to go through a little bit of question time. Actually, before we do question time, before we have a break, so we'll do question time. So we'll do a little promo, which will take 2 minutes, and then we'll do questions, and then we'll take a quick break. So essentially, quick promo because we need to do a little bit of a promo. So as I said before, I work for a company called ShootSmart. ShootSmart is a tutoring company built from ATAR notes. Essentially, what I do as a tutor is I run a chemistry 3-4 class. I run the Thursday class from 6 to 7:30. We did have another medicine student doing the Saturday one. I'm actually not sure if she's doing it next year or if she's doing a different topic, but I assume she probably still is. But you get 2 medicine students. She's going into final year. I decided to do an honours, so we were in the same year level. I'm now going to finish a year after her. But essentially, this class runs for an hour and a half every week. We go through we have like PowerPoints every week, but essentially it's like a big class discussion. So we run it on Zoom, and I go through some content. We go through some practice questions. I go through sort of the answers. I look at your answers, like you can send them through, and I go, hey, like this is what you need to change. This is what you need to do a little bit better. This is what I really like. And essentially, we go through sort of content like that. We go through each week, and we go through in depth what the topic is each week, and we cover things, ensuring that everyone sort of is on the same page and that there's no one sort of falling behind, there's no gaps or anything. And there's usually sort of 10, 15 students in each class, so it's pretty sort of intimate in terms of that most people, nearly everyone can ask questions and everyone can get the help they need. And essentially that's what happens every week in this class. There's worksheets with every class. I try and have SACs and exams made for each class. So Chemistry 3-4 definitely does, because we're at the final year of the study design. I've been making those SACs for 4 years. I've been making those exams for 4 years. So we definitely have our own exams and SACs, and we go through those as well and go through exam tips and so forth. And usually most of the students in my class have my email and email me whenever they have questions. So that's sort of how my sort of Chemistry 3-4 class works. We have them for all our subjects. And they all run slightly differently, but that's sort of how I run my Chem 3-4. And then we have one-on-one tutoring. Now, this box here is meant to be what subjects do I one-on-one tutor. If I were to one-on-one tutor, it would be further biology and chem. I don't do methods anymore. But I unfortunately don't offer one-on-one private tutoring. That's just because my uni is so busy. I don't really have time with uni to do the one-on-one tutoring. However, many tutors do, and we have many tutors who are probably far better at chemistry than me. So go see them. But essentially our one-on-one tutoring is you pay per hour or per half an hour. I think it's per hour, and you just you book in with a tutor, and essentially you can book in any time. You usually get their email. You can just email them like, hey, are you available at this time on this week? And I'll book you in. And it's sort of like just having a private tutor, but through TuteSmart. And so therefore it's kind of, you're running it through the company. You can always know that there'll be a tutor available. And if your tutor's not available, you can go with a different tutor. And you can get tutoring for any subject. We have tutoring for nearly all of them. So essentially that's one-on-one private tutoring if that's what you want as well. So now we're going to go to questions. We're going to do questions for till 10. We'll go to 11:15, and then we will take a break. So what I'm going to do is the first couple of questions I'm going to leave. Now, why is that? Because I think they're probably the highest yield ones, so we'll answer them at the end. So we might jump down to here. So those top three, keep upvoting them if you want them, but I'm going to answer them at the end of because we have another question time at the end. So how much background knowledge from year 11 is assumed in year 12? If you don't remember, year 11 chem content should be revised. So that's what I sort of talked about at the start. So there is a lot of assumed knowledge. Moles, stoichiometry of chemical equations, assumed knowledge. Moles, assumed knowledge. Intramolecular bonds, assumed knowledge. HPLC, which is getting cut, but it's still in for you, is assumed knowledge. Really important, you need to know your HPLC. Titrations, we have a class specifically on them, but I know a lot of schools don't go through it, but assumed knowledge. Even though it is sort of in the study design, it's assumed knowledge from year 11. So if your school doesn't go through it, something you may need to revise, but titrations is a really big thing. So there's titration curves, etc. With HPLC, it's less about HPLC, it's more about the calibration curves. What else is assumed knowledge? Organic, you go through all completely new. So it's kind of assumed knowledge, but like you're going to go through it new. It's probably about it for now. Redox basics as well, maybe assumed knowledge, but the rest of it is not. So things like pH calculations, they're gone. Things like, there's a little bit of, I'm just trying to remember some of my head. Things like number of molecules very rarely comes up. Things like those S2, P2, like the valence shell electrons. I haven't done 1-2 chemistry in a very long time. I've actually been reviewing it a bit because I've been updating their content because it's become very more 3-4 based. And the new content is a lot more fun than their old content. That's all I remember. That stuff's not there, the S2, P2. That stuff's not in 3-4. What you'll find is that as you go through the year, the assumed knowledge, you'll just sort of pick it back up. So I wouldn't worry too much unless you really struggled. Like let's just say, for example, redox. As much as you go through it again, if you really, really struggled in year 11, it might be worth revising it now. Why is that? Because they kind of assume that you have a base knowledge and therefore they make the questions a bit harder. So just important that maybe you go back over those things that you really struggled with. It's a good question. I would suggest if you struggled in areas that do come up in 3-4, that you go over them again. What was your favorite study technique? What was my favorite study technique? Was not studying. No. My favorite study technique. It's a great question. I probably enjoyed practice exams the most, but that's the end of the year. For now, I think my favorite was probably summaries. And it sounds a bit backwards, but I enjoyed, so what I found was best for me was if I had a class, let's just say I had chemistry and biology that day. I'd come home, I would summarize what I did in class. So I would try each night and summarize what I did in class. Like, yes, this doesn't work for things like maths and English, but it works for science subjects. Science subjects, this is great. Come home, summarize what you did. So I had a little summary book. I don't think I have it on me. If I did, I would show you. But I had a little summary book. It was literally like a little notebook, but it was really thick. biology, my summary book was like an A4 and ginormous because there's so much content. But chemistry, I had a summary book, and every night after class I'd come home and I would summarize the content. I'd try and summarize it in a little page, like a little like two-fold page, so it ends up being like the size of probably an A4. I'd try and summarize that class in that sort of page. I would therefore then do that, so that would be the first set of revising. I would then every sort of weekend after the week, if I wasn't super busy with like assignments or I had a SAT coming up or something, I'd try and do some practice questions from just a resource. So my school gave a lot of board exams, and what my teacher did was she cut up those board exams and essentially had them broken down into each topic question, so the older ones, not the newer ones. That's something you could do, is if you have lots of company exams, or a really good resource, which we'll talk about in a bit, is sort of the ATAR note topic tests or the ATAR note study designs. They have some really good just like questions for that topic. And essentially what I would try and do that weekend is then I'd try and do some questions, and I'd look back at my summary, do questions, look back at my summary, change my summary if I needed to, go back to those and do those questions on that topic. So essentially what I was doing was I was re-reviewing that topic as much as I could, because that re-reviewing that topic was essentially how I was going to learn. It was all about sort of retouching on that topic. So if I saw it in class the first time, I'd summarize it the second time, do some questions on it, that's the third time. That's sort of how I did, that's kind of what my study technique was. Probably not overly helpful. I probably wasn't the best studier in the world. So I do apologize if that wasn't overly useful. I hear this a lot. I'm really bad at chem. Like, nothing makes sense. How do I get at least some understanding? So I think what's really important, first step for anyone who thinks like this, is take a deep breath and just find a little bit of confidence, because chemistry is hard, and you're doing chemistry, which means you are either working really hard or you are a very smart person, because chemistry is really hard, and you should all, if you've all survived 1-2, you should all be extremely proud that you've gotten here, and then at the end of the year you're going to be even more proud of yourself, no matter how you go. Chemistry is just hard. Like I can't sort of make it any easier for you. I'm trying, like, as I said, these classes are here to give you knowledge and to work it through with you. However, chemistry is difficult. What I would say, if you think nothing is making sense, have a chat with your teacher about or if you have a tutor, what areas you're really struggling with. If it's the stoichiometry, if it's the, let's just say it's the gases or it's the fuels, have a chat and get some resources. So what's really important is, as I said, summarizing things, but then doing questions, and not doing textbook questions, doing questions that are written like an exam. Because if you can do questions that are written like an exam, you're understanding the knowledge, because you're able to teach, you're sort of like teaching the examiner. That's how exam questions are presented. They're presented in a sense of you're sort of teaching the examiner the topic. So if I'm able to sort of put that back out there, then you'll do really well. I think what's really important is, first of all, just have some confidence in yourself. I'm sure you're doing really well. And as much as you think nothing's making sense, you probably know far more chemistry than those who don't do chemistry. So you're already one step ahead. Just take that deep breath, do some exam questions. Don't do VCO ones. Do sort of try and get some ones, maybe like, as I said, the ATAR notes, topic tests. If you only have a textbook, do textbook questions. That's okay. But practice just getting the knowledge out of your head back onto the page. That's probably my best tip there. So this one has jumped up. What grades did you get in order to get a 4? That's a great question. I did year 12 5 years ago. I'm old, I know. So I actually don't remember what my SAC marks were or anything. I don't actually know how the grades work in chemistry in terms of what percentage. I know overall my exam marks were A+, and then my SAC marks, like, you know, at the end of the year, you get 3 letter values, and then you get your number, you get your raw score, and then you get your score. I know my 3 were A+, 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 but I know people who got a 38 or 39 and all had A+, A+, A+. So it's kind of deceiving. Like they got a 38 and a 39, they had A plus, A plus, A plus. I got a 44 and I had A plus, A plus, A plus. So I don't actually know the values. Apologies. I think that, and they change every year, but I think you've just got to be working hard. Chemistry is difficult, and to be honest, my 44 scaled up to a 48. So that shows how difficult it is. It scales up nearly as much as methods, which I thought was one of the most difficult subjects I ever did. So that's just how that works. And then, all right, final question, because we want a bit over. Which topic comes up the most in the final exam? Great question. I would say they all come up fairly equally, you'll find. Organic, there's always a 10, 12 marker. Experimental design, the last few years has been increasing. It's increased from like 10 marks to 16 marks. Spectroscopy, there's always at least 10 marks on. Like, they all are pretty equal. Just food chem's always really low. Food chem's only ever like 4, 5, 6 marks. Whereas all the other ones at least have 10 to 12. So that's probably my answer to that. All right, let's go take a break. So we're going to take a break until 11:25, I think, is a fair time. So I think that gives us about 7 minutes. So let's take a break till 11:25. We'll then have 65 minutes left to pump out the rest of our content. We have a little promo and then we have some content. And then we'll have some tips at the end and we'll do some more questions. But I think 7 minutes or 6.5 minutes is a great amount of time. Just go take a break, go to the toilet, stand up. I will be back at 11:25, so go take a break. So, hopefully everyone's back. We're going to jump into topic 2, which is electrochem, which is redox, which I'll be real with you, is my least favorite topic. It was my least favorite topic at high school, and it's my least favorite topic now that I tutor it. But it's important, and it's always worth a few marks. So, or as I said, most of the topics are worth sort of that 10, 12 mark range. This will be worth the same. So, just before we start, a couple of promos. So, Ed Unlimited. So if you haven't heard of Ed Unlimited before, it's essentially, I'm sure you've heard of these books before. I'm sure you've heard of the ATAR Notes topic tests and the ATAR Notes study guides and the text guides. These are really good. I used them when I was in year 12, which is 5 years ago. And they were awesome. I loved them. I had them for physics and I had them for methods. So the two subjects I used them for. And I loved them. Ed Unlimited is essentially the same thing. However, you get them online and you get access to all of them. So, with the books, you buy an individual book. With Ed Unlimited, you pay sort of a monthly subscription. It's very low. And essentially what you get is you get all of the books online. You also get all of the NEEP content. So NEEP is a company which makes exams. NEEP was bought out by ATAR Notes in about just before COVID, 2020. So all the content from them, essentially prior to that, was by NEEP, and now it's sort of NEEP by ATAR Notes. NEEP is still a separate company. However, being under ATAR Notes, we kind of have a bit of say in it. And their exams have become really good. I think their exams beforehand were great. They're even better now. And you get all of their content. So they have practice exams every year. They also have their own study guides, and they also have their own those question booklets. They're like textbook questions, but a little bit more exam-based. They're a little bit better than textbook questions. They're sort of in between. They have that there, and there's text guides for year 10, 11, 12. So if you're year 11 doing 3-4 Chem, you get all the year 11 1-2 ones as well. Essentially, what we're offering now is a free trial, and a free trial of 21 days, so you can cancel it before the end of that and not have to pay anything. And the code there is JoshVCE. If you're attending any of the lectures this week, you'll hear some other codes. They don't work. Mine's the only one that works, just an FYI. So you need to use JoshVCE. You're welcome to tell your friends, and they're welcome to try it out as well. And I think it's worth a try. It's probably the best time of the year to give it a go as well. It's valid until the 31st of Jan. Obviously, the 21 days goes beyond that, but it's valid to use until then. But I think it's the best time of year to use it because you can use it now and see if you like it. And if you really like it now, it's worth keeping going through the year because you will use it. And I use those topic tests, and that's the best code there. So JoshVCE, you're going to use that code. You're not going to use anyone else's code. You're only going to use JoshVCE. That's just an FYI. So it's JoshVCE, just an FYI. And then we have a book offer. So if you really like a hard copy book, we still offer them. They're still available. At the moment, we're offering them 15% off until the end of Jan if you use 15 Jan at the checkout. So essentially, it's all the same books. You just order them online, and we'll do a big sort of. They'll all get shipped out this week because given these lectures, there'll probably be an influx of orders. So that's there as well. So that's sort of the last two promos we have. So moving on to electrochem. So essentially, we have 50 slides of electrochem. Not even. I think we go a little bit into equilibrium, but essentially redox. In year 11, you did a lot of acid base, and you did a little bit of redox. And redox is redox. It's just difficult, and it doesn't get any easier. But it's something you just got to push your way through. Redox in an exam is always quite tough, but it's always reasonable. It's tough, but it's reasonable. The marks are there. If you sit down with it long enough, you can figure it out. And so that's the really important thing with redox, is that as we go through all our redox content, it's going to be hard. But my biggest tip to all of you is to sort of keep pushing, keep thinking like, I can get the answer to this, because you can. Everyone can get the answer to the redox questions. They are difficult, but the answers are there and you will get them. You've just got to keep pushing your way through. So redox basics, as we said before, it's acid base. It's a transfer of electrons. I'm sure you've heard of this before. Oil rig. Oil refers to oxidation involves loss, and rig refers to reduction involves gain. And essentially these are the two sort of basic half equations that you get from them. So redox basics. In a redox reaction, one species is the oxidant and the other is the reductant. So terminology matters. So oxidant causes oxidation of the other species, but is itself reduced. So this can be really confusing. So if I'm the oxidant, I am causing you to be oxidized, but you are all causing me to be reduced. So it's like a teacher. A teacher teaches you. The teacher itself doesn't get taught, but you get taught, because the teacher is doing the teaching and you are being taught. So you are being oxidized by the oxidant. And then the other way around, the reductant causes reduction and is itself oxidized. So that can be really confusing, but I think the best way to go about this is to just write it down and then don't think about it too much. The more you think about it, the more you get confused. This is one of those things, it's like the opposite. Look at it once or twice and that's it. The more you look at it, the more you will get confused. So redox basics. Essentially what happens is you have an electron, the electron moves, and then you get some changes. So the electron was lost from here, so A underwent oxidation. The electron was gained here, so B underwent reduction. A sent an electron to B, therefore it is called the reductant, whereas B pulled the electron from A, and therefore it is called oxidation. So what's really important is they occur together. We can't have one without the other. Yes, we look at things in terms of half equations and in terms of what is happening in half the reaction. Yes, that happens, but we don't think of it in terms of oh yeah, this is happening separately. They all happen together. We just look at it in separate manners because it allows us to unpack what's going on better. The electrons lost by one species, they have to be gained by another. It's like the energy conservation sort of reference. Electrons have to be conserved. So oxidation states. This is how we know if we're going through reduction. So unlike the diagram we saw before, we don't explicitly show the movement of electrons in the chemical equation. How do we determine if it's oxidation? So we look at oxidation states. And they're simply a tool to keep track of how electrons are moving. So let's have a look at this. So few simple rules. I'm sure you went through these last year, so these are probably revision, but oxidation states of free electrons are 0. So chlorine gas, helium gas, sodium, solid sodium, or solid iron. You've then got the ion versions of these. So you've got chlorine ions, or chloride ions, you've got sodium ions, you've got magnesium ions, nitrous ions. And then in compounds, there's a few separate rules. So the main group metals have the oxidation states equal to the charge of their ion. So sodium stays +1, magnesium stays +2. Hydrogen is almost always +1, and oxygen is almost always -2. There are two There are two examples I want you to know. I always forget the hydrogen example, so I'm going to forget that one, but I always remember the oxygen example. So the only occurrence where oxygen is not -2 is H2O2, which is hydrogen peroxide. Now, hydrogen peroxide, you've probably heard of it before. It is a poison. It was used during World War II a lot and is quite dangerous, and that's why it doesn't really exist in this state unless it's forced to by chemists, and that's why it's a poison. So, essentially, H2O2 +1, which makes this +2 overall, and -1. So -2 overall, but the individual atoms are +1 and -1. So in this case here, it's -1 instead of -2. That's the only time that it is that way. Now, the hydrogen one is like, it's like HF or something. No, it's not HF, it's something. I forgot off the top of my head. The hydrogen one has never come up in a VCAR exam. Hydrogen peroxide, the oxygen one, has come up before. So the only examples you need to know. The sum of all oxidation states must also equal the charge in the species. So CO2, what's the charge of the species? It's 0, it's neutral. So if we have -2, so we've got overall -4, therefore the other one needs to be +4, because +4 plus -4, which is what it would be overall, equals 0. Over here, we've got a -3, so overall we need to equal -3. So we have -2, 4 times that is -8, so we need to finish at -3, we're going to have +5 as our phosphate. Same thing here, look at it like that. So there's some really good examples. So which of these is redox? Well, +2, -1, +2, -1, that's not redox, there's no change of electrons. We've got some more here. Do we have a change? Doesn't look like we have a change, not redox. All right, we've got 0, we've got 0, we've got +3, we've got -1. Have we got a change? We do, we have a movement of electrons. Therefore, not redox, not redox, redox. So our last equation here is redox. Those first two are not redox. So if oxidation state reduces, then the species has been reduced. If the oxidation state increases, it's been oxidized. So that's another way of thinking about it as well. So determine whether or not the following reaction is redox. If it is, identify the reductant and the oxidant. I want everyone to take 1 minute to have a go at this one. Take a minute, have a look through, and write down what you think. All right, hopefully I've given you enough time. So, is this redox? Well, I think it is, because I'm asking for the reductant and the oxidant. So 0, well, this is going to be -2, and then this is going to be +4. This one here is going to be +6, so therefore this is going to be -3. Here we got +1, we got -2. So we've definitely gone through redox, and then if we look at it here, oh yeah, I put down the full values. Apologies, I should have put down the half values. The individual atom values, sorry. So for things before, it's combustion reaction. Oxidation states change, so the oxidant is the O2 and the reductant is the C2H6. Now, you might say to me, why is the reductant the whole molecule, despite the fact the carbon is the only thing that is oxidized? That's because we think of it as the whole species. You can't really just have the carbon there by itself. You need to have it there as a whole compound. So having the whole compound there acts as the reductant. Even though it's specifically the carbon doing the reducing and itself is oxidized, it's the whole species, if you think about it. The whole compound has to be there. Hopefully that sort of makes sense. So balancing half equations. This is another thing that's really important. You'll be asked to write out half equations all the time. You'll be told this becomes this, give me the half equation. So as you can see here, this is just an example of sort of the two half equations within one. So we've got a combustion reaction just from before. This is ethane. And so as you can see here, we said that ethane was being oxidized and our oxygen was being reduced. So as you can see here, oxygen goes to water, ethane goes to the CO2, and then you just added in hydrogens, electrons, hydrogen, electrons, and you had your water there. Ended up with the full equation. Now, what's really important is, how did we get those half equations? We use this thing called the Coase method. So, the Coase method. The Coase method stands for key atoms, balance the oxygen atoms. So, balance the key atoms, so all atoms except for H and O's. Balance the oxygen atoms by adding H2O to the opposite side. So if you've got oxygen, you've got too many oxygen atoms on the right, you're going to add some H2Os to the left to equal out the oxygens. Don't worry about the hydrogens at this point, you're just going to equal out the oxygens. Balance the hydrogen atoms by adding H plus ions, and then balance the charge by adding electrons. So you're going to add H plus ions, and then that's going to balance out the hydrogens, and then you're going to balance out the charge, because when you add these in, they're going to increase the charge on one side. And then you're going to add electrons to balance the charge, and then you're going to add the states. So that's the Coase method. So we have an example here. We start off with these two molecules here. So we've got dichromate and we've got chromium ions. So dichromate to chromium ions, what are we going to do first? K, key atoms. We've got 2 here, we're going to need 2 here. Then we go O. We've got 7 here, we're going to need 7 H2Os over here. We then say, all right, hydrogens. I have 14 here, I've got none here, so I'm going to need 14 on the left side. Then we look at charge. I have a charge of 14, 12, and I have a charge of 6. So 12 over 6, I'm going to need 6 electrons on my left side. So I need 6 electrons on my left side. And then states, you just add all your states in. Electrons don't have states, by the way, so never add states onto an electron. Now, this question here was a VCAR question. VCAR 2016, 2 marks to go through this method here. And this was the answer they wanted, and this is how they wanted you to go about it. You don't need to show the steps. You don't need to show, oh, I did K, and I did O, and I did H. This full answer will get you 2 marks, just writing this down, because they know that you had to go through a method to get there. You can't just put this one on there without doing something. So this is one of those ones where they allow you to just sort of write down the answer. If it's all balanced with the correct states, you're going to get 2 marks. So that's how you do that. So another practice question. I think it's good. I think we do some practice questions, and I think get your mind working. So everyone to have a go at this. This is going to be difficult. If you haven't ever done the Coase method before, you'll find this difficult, and that's okay. But have a go at it. So we've got K, O, H, E, S. Have a go at the Coase method. And have a go at this one here. I'll give everyone a minute and a half. So what do we got? We've got till 11:44. Have a go at this one. All right, that's 11:44 now. So let's go for this one. So first of all, put out your key ones and balance them. I don't need to balance anything here because if you notice, there's 1 and 1. So we skip the K step. There's no need for it. Oh, I have 3. I have 4. So I'm going to need to add 1 to my left side. I added 1. Hydrogens. I had 2. I have none. So therefore, I'm going to add 2 to the right side. My charge. I have a charge of 0. I have a charge of -2. So -2 on the left. 0 on the right. I'm going to add 2 electrons to the right. States, aqueous, liquid, aqueous, aqueous. Done. So you might ask me, states, how do you go about the states? If in doubt, it's aqueous. Water, always liquid unless they tell you it's a gas. That's about it. The only time you really need to go digging and have a look around is if you're working with combustion reactions and you got your fuels. Look in your data booklet, because as I said, on the data booklet it says, it gives you the values and it gives you the state that it's in. Make sure you use the right one. If you don't use the right one, you may not get it. So that's simply how you go about this question. This would be a 2-mark question. Yes, this one was considerably easier than the last one. This would still be a 2-mark question. It's a free 2 marks, that's what it is. Because the more you practice this, you're going to be speedy at this. This is going to be a sort of question you see and you're like, yes. 2 free marks and I can do it inside a minute. And you'd pump this question out inside a minute. 2 marks, you've saved yourself time and you've got 3 marks. These are great questions in exams and it's something that I want all of you to be on top of. So now what we're going to move on is to the next step. So now we're going to move on to a galvanic cell. So I'm sure you've seen these before as well. So if we have sodium solid, as you can see here, this is a redox reaction. You put them in together, sodium inside water goes boom. However, this is only chemical to thermal energy. This is a bit useless. As much as this is oxidation and reduction and redox, it's a bit useless because what are we going to do with that? Nothing. What if we wanted chemical to electrical? We would need to separate things. So what we need to do here is we need to separate things, because if we think about it, energy is actually the transfer of charge. It's the transfer of the cations. So it occurs via the electrons. So if we move electrons through a wire, we get electricity. And we move electrons in a redox reaction. So why don't we force the redox reaction to happen through a wire? That's where a galvanic cell comes in. We force the redox reaction to occur through this wire, and in doing so, we produce electricity. So, galvanic cells are in everything. Your phone has a galvanic cell in it. Your laptop has a galvanic cell in it. Your camera has a galvanic cell in it. Your watch has a galvanic cell. Everything has galvanic cells in it. Your car has a galvanic cell in it. It's simply any device that converts chemical energy to electrical energy. Anything with a battery in it is chemical to electrical. What's really important is that a cell is an individual galvanic reaction. It's an individual set that has this chemical, and a galvanic cell in it. A battery is lots of those cells together. So your phone will have loads of them. That's essentially how that works. So if we look at this before, we said oil rig. We said oil rig, oxidation involves loss, reduction involves gain. Now, we start to think about things called an anode and a cathode, and I'm sure you all know what they are because you've been through this before. But an oil rig cat is our new saying. Anode at oxidation, reduction at cathode. So it actually should be the other way. Oxidation at anode, reduction at cathode. So an oil rig cat. I also like to think of it as an oil rig happy cat, because cathode is positive when we are spontaneously reacting. So key terminology. We have 2 half cells. We have 2 electrodes. We have an electrolyte. We have an external circuit. We have a salt bridge. Now, in this example here, we don't have anything down. So I'll just say, if this is the positive side, if this is the positive side before, I said when we're spontaneously reacting. So I'm going to say this is spontaneous. This is spontaneous, and thus we have a positive reaction on the left side. The positive reaction will be the cathode, because the cat is happy. And what happens at the cathode? is reduction. So what will be happening here is reduction. So this will be the reduction half equation. On this side then, it'll be negative. It'll be the anode. And it will be the oxidation half equation. Another way of remembering this is that you have consonants and you have vowels. That's another way of remembering it. The other thing here as well that I always like to think about is AO, Australian Open. Don't know why, I just always think about it. AO, Australian Open. It's just one of those things I always remember. And it's just how I kind of go about it. Now, one other really important thing that we will discuss in the next slide, but I think it's important we discuss it before we get into the example version of it. The salt bridge. Now, the salt bridge doesn't directly transfer electrons. However, if you pull that salt bridge out, it won't work. This whole thing will stop. There will be no electron flow between the circuit. Now, why is that? That's because these electrolytes need to be very neutral. They can have a little bit of charge, but they need to stay at a constant neutral charge they feel comfortable at. How do we do that? Because if we think about it, let's say in this example here, so at the cathode, we've got a positive charge. What are we doing? We're gaining electrons. So in this one here, we've got electrons coming in, and if we have electrons coming in, we've got, let's just say it's Zn. I'm just trying to think of an example off the top of my head, sorry everyone. So we'll have Zn2+. We have Zn2+ in here. As the electrons come in, the Zn2+ goes onto here and becomes Zn solid. Essentially, that's just what's going to happen in this example I'm giving you. What's going to happen is, with this 2+ charge becoming nothing, what's going to happen to the charge in this half cell? This is going to reduce. That's what that is going to happen. So that we're going to lose charge. This is going to become less neutral. It's going to become more negative. And this half cell is not going to like that. So what the salt bridge does is it has a molecule here. I like to use KCl, but there are a lot of other ones. You can use, actually no, I like to use KNO3, sorry. KNO3, I don't know why I use KCl. KNO3, and essentially what happens is the cations, which in this case here would be K+, get pulled from the salt bridge into this half cell. The NO3, which is the anions, get pulled from the salt bridge into the other half cell. And essentially what happens is, if you think about it, the negative goes towards the negative and the positive goes towards the positive. And they allow this to stay neutral. They allow both sides to stay neutral. And that is the role of the salt bridge. You take the salt bridge out, the neutrality is lost, and the whole circuit stops. You haven't got a complete circuit, it stops. So you need to make sure you have a salt bridge, and an appropriate one. KNO3 is a great one. So, example here. This is why I flicked across box. I needed an example. I don't know why my head was like, I cannot think of an example right now. Galvanic cell example. So we've got zinc, and in this case here, we've actually going the opposite way. We've got zinc going from zinc solid to zinc 2+. In the other half cell, we've got copper 2+ going to copper solid. So in this case here, this one will actually be the anode, because the zinc is being oxidized, because this is 0, this is 2+, that is increasing, therefore we have oxidation. We also have an increase of Zn2+ coming into this space here. So what do we think is going to happen with that? Well, we need anions being added, as you can see there. We need anions being added because as we get more positively charged, we need anions to come and compensate for that. On the other half, we need cations. As you can see here, we're going to start to lose the solid here, and we're going to gain more solid here. Electrons, they're always going to flow anode to cathode. It sort of makes sense. They go from the negative side to the positive side because opposites attract. So then electrons will always go from anode to cathode. So always think electrons, they go from anode to cathode. Anode to cathode makes sense because oxidation involves loss. We're losing the electrons to the cathode, which is reduction, which involves gain of electrons. So think of it like that. So Anode, it's the site of oxidation. It's the negative polarity in the galvanic cell. The cathode is the site of reduction. It's the positive polarity in the galvanic cell. Key point, polarity is unequal charge. The polarity is this here. The charge within this is where we talk about the cations. They're slightly different concepts. What's really important as well is the concept of anode and cathode, and you putting something there and saying that's the anode or that's the cathode. So notice before how in this example, zinc was being oxidized. And if I go back here, I said here that zinc was actually being reduced. That's because they can do both. Like most of these things can do both. It just depends on what their partner is, and we'll discuss that in a little bit. What the important concept I'm trying to get at here is that when I put this here, when I put this big chunk of zinc here, I don't say that's going to be my anode. What I say is that is an electrode. Essentially what's going to happen at that electrode is whatever I put in here and whatever I put in here is going to determine whether that is an anode or a cathode. The anode is only where oxidation is. If oxidation is occurring, the electrode becomes the anode. If reduction is occurring, the electrode becomes the cathode. You call it an electrode, and then once something starts to happen, you give it a name. So it's like saying you have a park, so you have a big park. I play cricket there, it becomes a cricket ground. I play football there, it becomes a football ground. I play soccer there, or football still, I call it soccer/football field. Like, it's the same spot, but as soon as I go and do something on it, I call it that. So, you know, if I go and play lacrosse on it, I call it a lacrosse field or hockey field or whatever you want to call it. Whatever sport I'm playing on, I'm calling it that. Same thing applies to galvanic cells. If that electrode is placed and it starts going through oxidation, I call it an anode. It's not an anode before that. It's only an anode when oxidation is occurring. If oxidation stops occurring, it's just an electrode. That's really, really important. And it's a really important terminology when it comes to VCAR questions in how you sort of write your questions and how you answer your questions. So, galvanic cells. As you can see there, it's to prevent electrodes from becoming charged. Cool. That's what we've already discussed this stuff. The one thing here that we haven't discussed is that the material used in the salt bridge needs to be unreactive and highly soluble. That's why KNO3 is a really good example. Awesome. So, if you have a direct reaction, you get thermal. If you have a galvanic cell, which is an indirect reaction, you get electrical energy. We like that, and that's what we want. So, here we have a very cool galvanic cell. Now, why is this a cool galvanic cell? That's because we have an inert electrode. Now, what I mean by an inert electrode, if you have a half equation here where a gas is formed, and a gas is essentially what your electrode should be. That should have been your electrode. But in this case here, we have a gas. You can't really have a gas as an electrode. So we need to make it work as an electrode. So what we do is we have this cool device where we put an inert material as the electrode. So the inert material is usually like graphite or platinum. These things don't react. However, they can act as a catalyst to a reaction. They can act and allow something to act in its place as the electrode, whilst it just is the physical electrode there. So, in this case here, I like to think of it as, I'm not sure how many of you sort of I follow the NBA quite closely, and in the NBA, a lot of their stadiums over there, they can convert them overnight from a basketball court to a hockey stadium. A lot of the ones closer to Canada will do that. So I sort of think of it like this electrode is the stadium, and then the gas is like what we're putting on the court. Are we putting a basketball ring there, or are we putting a hockey stadium, like a hockey court there, or whatever they call it, hockey ring, is that what they call it? Essentially, that's kind of how I think about it. So I'm just trying to refer to real life examples. You have a stadium, and then it depends on what you put down as to what you play. So what gas am I putting in there is what's going to act as my electrode. So in this case here, the hydrogen gas is acting as my electrode, even though I have an inert electrode in there, which would be, platinum, or it would be platinum or graphite. And we call the platinum or graphite the cathode, even though the reaction is occurring through the H2 gas, because that's what the physical thing is there. Now, my second point with this one here is you notice how instead of a light, we've put a little meter. And that little meter is pointing this way, which means that the current is going that way, which is what's happening, or the electrons are going that way, which is what's happening. The electrons are going that way. So the electrons are going from the anode to the cathode. And then it says here, negative 7.6 volts. That's how I am determining its charge. I'm determining what's going on. So it's negative 7.6 volts. What's really important is the negative refers to the direction. It's like our delta H's from before. You cannot have a negative voltage. It doesn't exist. That is still 0.76 volts. It's just that it's heading in the opposite direction to what the reader reads in. So this thing is like a voltage reader. It reads in this direction. So when the charge goes this way, it says, oh, I'm in the negatives. It's negative 0.76. But it's actually just a positive voltage going the opposite way. So it's just the direction of the voltage, really important. So it's a 0.76 voltage. And you'd say, how did you determine that? Well, we can determine that, and it's actually quite easy to determine. So a galvanic cell is able to generate a current, and as the electrons move, we say that the potential difference exists between the two half cells, and that potential difference gives us the voltage value. So we can measure the potential difference of a single half cell called a standard electrode potential. And we do this by connecting every half cell to a standard hydrogen half cell. So if we compare everything to a hydrogen half cell, we can say this is what the standard electrode potential is. And so as you see here, the zinc half cell is a negative 0.76. As you can see here, we have the PB one, and the PB gives us negative 0.13. So our lead one here. So our lead gives us negative 0.13, but our zinc gave us negative 0.76. Thus, we conclude that lead is a weaker reductant than zinc. And we'll discuss that when we get to, where is this? Yeah, here. This is the other slide I was looking for. I was like, wait, is there another one? And then as you have here, we have silver versus hydrogen. We get positive 0.8. What that means is that our silver is actually on the opposite side to our hydrogen. And it has swapped things. So in this case here, back here, our hydrogen was always the positive cathode. It's actually become the negative anode. And the silver has become the positive cathode. So what I mean by that is this here. This hydrogen is the standard. It's the middle. It's 0.0. Why is that? Because if we compare hydrogen with hydrogen, nothing happens because they're the same thing. So if you look at this here, you have the strongest oxidant, you have the weakest oxidant, you have the weakest reductant, you have the strongest reductant. What that means is that this here is always going to cause everything to be reduced that it goes with. It wants everything to be reduced. Whereas this one, wants everything to be oxidized. Wrong language. This thing wants everything to be oxidized. Everything that goes with it is going to end up being oxidized. On this case, the lithium solid, it wants everything to be reduced. Anything that goes with it is going to be reduced. These two are highly reactive because they're at the bottom ends, at the top ends of their strength. Whereas these two are the opposite. They're really, really poor at causing other things to be reduced and other things to be oxidized. And as you can see here, this is from your data booklet. These are the values that were obtained when comparing with the hydrogen half cell at SLC conditions. And as you can see here, these ones were positive, these ones were negative. So these ones just went in opposite directions. When these ones were in here, this was the cathode. When these ones were in here, this became the anode. It just depended on the strength comparative to it. And what we can utilize from this is we can figure out our value. So we can figure out how much voltage are we going to get out. So when we compare the hydrogen with the nickel, we get 0.25. But what if I compared the nickel with the copper? Well, what you look at is the difference. Well, if I have 0.34 and I have 0.25, what you do is you technically take away the 0.25, but because it's a negative value, you end up adding it on, and you get 0.59 as your difference between those two cells. So you're going to get a difference of 0.59 volts. So that's what you're actually going to get when you compare those two. And that's how we determine what we're going to get out and how we get our electrode potentials. So we've seen that the following reaction will be able to be used in a galvanic cell to generate electricity. So what if we replace Cu2 plus with Mg2 plus? Will we still be able to generate electricity? No. Why is that? Because we need to look at our series. So if I have zinc solid and I have copper 2 plus, I have top left, bottom right. So I have a really strong oxidant and I have a really strong reductant. Tick. That's going to work. That's going to be spontaneous. We're happy with that. If I have Mg2 plus, I have a really weak oxidant now. And I still have a strong reductant, but my weak oxidant isn't going to be strong enough to deal with the zinc solid. Therefore, from going bottom left to top right, that's not spontaneous. I'm not going to get a reaction occur. There will be no spontaneous reaction occur. If I want this to happen, I have to force it. And that's not what we're looking at here. We're looking at what will happen spontaneously. So Mg2 plus to Zn solid is not going to happen, whereas our Cu2 plus and Zn solid will happen. And it's the top left, bottom right. Now, what if we have multiple things? Well, what we talk about here is you always choose the strongest. So even if I had this as well, I would choose this over this, and I would choose this over this. Because, the other way around. Because that one is the strongest oxidant and that one is the strongest reductant. So you always choose your strongest reductant and your strongest oxidant. So top left, bottom right, and you always go highest left, highest on the right, or lowest on the right. So again, the other thing is SLC. We've already discussed SLC. You have to be at SLC. Really, really important. This was all done at SLC, so we need to be at SLC. And as we talked about before, calculating. So we do our E of our oxidant, take away our E of our reductant. Why is that? Because we always end up with a positive value. We should always end up with a positive value. When this one is higher than whatever one you're doing, even if it's two positive values, so you have 0.8 and you have 0.15, well, you need to take that away to find the difference. So you take 0.15 away, you end up with a difference of 0.65. Whereas if you take away a negative value, you end up adding it on. So you end up going 0.8 plus 0.13, and you get 0.93. So you always end up with a positive value when you use this equation. So this is the voltage of the cell, or the potential difference of the cell. So the potential difference. That's what we're looking at, the potential difference of the cell. Awesome. So we have a practice question here. I want everyone to have a go at this and see how you go. So essentially what we've got is a switch is being flicked on and it allows for flow through the circuit. Which of these will have the electrons flow towards it? So which way do electrons flow? Remember we mentioned it a couple of times. And what is the potential difference between the cells? So have a go at this one here. I'll give everyone maybe one more minute. Minute and a half again, total. Probably fair for this question. How much we got left? slides. All right. All right, so we're going to go through this one, and then I was just looking at what slide. That's why I've got my phone. I've just got the slides off my phone. We have about 10 slides on fuel and secondary cells. I think we're going to skip over that. I think we're just going to run out of time, sorry. But there wasn't a lot of detail on those. They were very much just like a very brief starter. So don't worry about that. We've gone through a lot of content today. Like we've gone through probably nearly a whole term, maybe a little bit less than a term of content, which is a lot of content considering we've been through in like 2 hours. Then we'll go over some tips. I think the tips and advice are really important at this point. So we'll go over them quite quickly, and then we'll jump into the practice questions jump into the questions just at the end. So go through this question here. First step, figure out what is the anode, what is the cathode. So you've got copper and you've got copper. So you've got, where are we? We've got copper and we've got copper. We have Fe2 plus, Fe3 plus. So we've got Fe3 plus, Fe2 plus, and Fe2 plus down here. But we don't have Fe solid. And platinum's not in it. So it's going to be this one, and it's going to be this one. So if we think about it, we've got, as you can see here, we've got the cathode and we've got the anode. So I'll get rid of my scribbles because my scribbles are just going to complicate things if there are already scribbles there. So we have the anode and we have the cathode. So anode and cathode, we have electrons flowing from the anode to cathode. That's how they always flow. So therefore, it's not going to be the copper electrode. The electrons are always going to flow towards the platinum. So we're left with C and D. Then we need to do the maths. 0.77, take 0.34. It's going to be 0.43. So we end up with C. And that's how you go about that question there. So it's a very typical practice exam or sort of typical VCAR multiple choice question. So that was from 2015, so it's a bit older. But as you can see, the exams back to 2015, 2014, 2012, they're all very relevant. They all still very much have very similar content and are quite useful in your study. So I think that's just an important point. So there's another practice question here, and there are solutions to it. You're welcome to go through it if you'd like. It's from 2008. That's how old these ones are, and they're still relevant. So that's sort of summary block 2. I then quickly put in some secondary cell stuff because I thought we might have time, but I don't think we will. So I'm just going to leave it there. So there's some fuel cell stuff, there's some hydrogen fuel cell stuff, and lots of fun. So let's move on to some tips and advice before we start so you don't end up shooting like that one down there. So just a couple of things, how sort of chemistry is assessed, just quickly. So essentially how chemistry is assessed is that, this is what each unit is worth, but I think what's really important is to sort of put an X through these. This is where it is all at. So what's really important to remember is that, for example, let's just say I go to one school, I do a SAC on fuels, I get 95%. You go to your SAC, you get 80%. However, if we swap spots and I sat your SAC, I would have got 70%. I would have got less than you. And if you sat my SAC, you would have got 100%. You would have done better in doing my SAC than what I did doing my SAC because you're a stronger chemistry student than me, but your SAC was just harder. That shouldn't be a disadvantage for you, and it isn't. So don't ever really get frustrated. If your SAC's really hard, don't get frustrated by that. If your whole class does really like average, don't get frustrated by that. It's all about ranking. It's all about where you rank in your class. So as long as you do the best, if you get 55%, but it's the best mark in the class, then it's practically like getting 100% because the exam standardizes that. So what's really important is that some schools have SACs really easy, and therefore you might think, oh, well, they're going to have A pluses for their units. Well, not necessarily, because if their SAC's really easy and then all their students do really bad on the exam, then it drags all their SAC marks down. That's what happens. The exam standardizes things. So it's all about ranking. Unit 3 and Unit 4, yes, your marks are important, but it's all about ranking. getting the highest sort of ranking within your cohort. That's what matters the most. So worry about rankings, and the thing is with rankings is you can't ask your teacher. I don't think you're allowed to. You're not allowed to ask your teacher your ranking, and that's a thing that teachers have. So you never will know your rank. You never should know your rank unless they tell you. It's just, you've just got to trust that you are where you should be, and you've pushed really hard and you've gone as well as you can, and you do the exam. And the exam will pull you up, because you've got to think about the exam as the standardized thing. So what's the deal with the exam? It's 30 multiple choice. It's 90 short answer. It's 120 marks in 150 minutes. It's hard. That's the reality. The chemistry SAC is one of the more difficult, chemistry exams is one of the more difficult exams there are. Please don't worry, like, the top end questions are there to split up those kids from getting a 50 and a 48. So please don't worry. If that's not what you're aiming for, then those questions are not what you're meant to be getting, like, right. There are questions in there that are purely there to split up that really top end. So there are some really hard questions. But overall, it can, I would call it a fair exam. It is hard, but it's a fair exam. You get a scientific calculator, so not the Casio. You just get the one with the little screen and then all the buttons, and a data booklet which they give to you. You don't get to take your own in. Exams all the way back to 2002, but not all questions are relevant, so you just kind of have to pick through what you think is relevant and what's not. So a couple of tips. Just to start out the year. I think what's really important is you print out a study design and you read through it and you tick off things as you learn them in class. Essentially, what will be on the exam is in dot point form, reference throughout the year, tick things off when you're confident, etc., etc., etc. Meet your new best friend, which is essentially the VCAR data booklet. Please, please, please print one of these off. Feel free to annotate one up. Feel free to use that one annotated as you go through the year. When you do practice exams, you'll always have a fresh one. You need to make sure you use a fresh one and one that doesn't have writing on it, because when you go on the exam, the one that they give you has nothing on it. It's just what is already printed on it. So you can't go through and you know what I mean, you can't take one that's annotated in. You can annotate it once you're in there, go for it, but it'll be blank when you get it. And as it says, you won't have time to be flicking through it looking for stuff at the end of the year. You need to know where things are. It's like a 14-page booklet. You will learn where things are. The more you use it, the more you will learn where things are. Use a scientific calculator. Really important. Practice using this, because this makes it so much easier. This makes calculations so much easier, but you don't get given this. So please, 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 please use this calculator down here. You're not going to be using this one up here. So, as it says there, get good with your scientific calculator. You can't use a CAS in the exam, so you need to practice. You need to practice how you play, in a sense. You need to practice how you would do an exam, and how you do an exam is with the calculator down here. Work hard, but work efficiently. Prioritize study that will have the largest possible impact on your result. Is that all I wrote there? So what I'm saying is, like, sort of prioritize things that you struggle on. And it's one of those things. It all feels good to do things you're good at. So you might be really good at equilibriums. And so you keep doing equilibrium practice questions because you keep getting them right and you're great at it. But then you're not very good at redox, and you're like, you do a redox question, you hate it. You're like, oh, I don't want to do redox again. So you just move on. That's not how you should work. You should be working hard, but efficiently. And what that means is focus on the areas you struggle with. So I really struggled with redox. Overall, I really struggled with English. So English was probably my weakest subject in year 12. So I focused a lot of time on it. I ended up getting a mark that was better than some of my other subjects because I spent lots of time on it. I allocated time to it. I went, I struggle with this. I need to spend time on it. So work efficiently, not just hard. And then do practice questions consistently. Please don't do VCAR ones for the last couple of years because you want to save those exams for the end of the year. You can go back a couple of years, maybe like 2016 down. Feel free to do those as you go through. Feel free to pick those exams apart and go through them. That's okay. But you should really be saving maybe 2016, 2017 onwards for when you do practice papers at the end of the year, because you want those ones to be like, all right, how am I going? What do I need to improve on? Where am I at? Et cetera, et cetera. So That's probably my one big tip. Otherwise, do practice questions consistently. Always touch back on topics that you've already done, so that you're sort of refreshing your mind, because you'll forget fuels really quickly. You'll forget redox really quickly. Equilibriums you'll forget quickly, because those things are Unit 3, and you'll move on to Unit 4 and you'll just forget about them. So always come back to them and touch back on them. And look after yourself. Take regular breaks. Be realistic about what can be done. Don't get like a study planner and put down 1,000 things for one day. You're not going to get it done. Make sure you keep doing what you enjoy. If what you enjoy is reading a book or going for a walk, or you play sport or you play a musical instrument or something like that, keep that up. Don't drop that because you're in year 12 and you think things are going to be stressful and you need to be putting 100% effort into all of just your studies. You need to make sure you still have a life. To be honest with you, uni just gets harder. And people joke about it, but it is true. Uni just gets harder. And so essentially you think year 12's hard and then things just start to get harder and you get used to it. And people will say, like, I'll say to you, I find uni easier than year 12 because I'm used to it. I know how to study. I know how to apply myself. I know when I can do things and when I don't need to do things. So I'm a much better studier now. But it's really important to understand that what can make things better is having a routine and not dropping things just because you feel like you need to study. Like, make sure you still have a bit of a life. Make sure you still go to those 18th birthdays and you still enjoy yourself. Year 12 should be a fun time. That's what's really, really important. And then good luck, but go questions. So we've got 10 minutes now. We're going to go through questions, and I did say I was going to go through these top ones, so we'll start at the top. So what was your approach to learning content? Did you take notes for class or do anything, or did you rely on class for learning everything? So I will be honest, I never took notes before class. I know a few of the students I've tutored over the years do, and it does work for them, but I never did. That was not what I did. You're welcome to do that if you want. I think it just depends on sort of how, as well, it sort of depends on your teacher. Like, if you love your teacher's teaching style, and I'm a strong advocate that there's not many bad year 12 teachers. Yes, you can say, oh, I didn't enjoy them. But to be a year 12 teacher, you need to be fairly decent at teaching. Yeah, there might be a few out there that are not the best, but most year 12 teachers are really good. It's when you struggle with a teacher, it's usually because their teaching style is just not the way that you enjoy it. And that happens. That's nothing you can do about that. If that's you and you're really struggling with the way your teacher teaches it to you, might be good to do this. Might be good to do some notes before class. Maybe the weekend before you go through the topics that you're going to go through in that week. Personally, I didn't. I really liked the way my teacher taught. I found it quite easy to follow, and I found that I just spent my time learning in class. I'd take a few notes down. I then went home and summarized it, and then did practice questions on the weekend, that sort of thing. When is the ideal time to start studying for the exam and other than VCE exams? All right, so doing practice exams, I would suggest, so my two things. I think you should do Unit 3 exams. Like, companies do Unit 3 exams. Do Unit 3 exams at the end of Term 2, or whenever you finish Unit 3, might be halfway through Term 2, whenever it is. I think they're really good. I think they allow you to revise really well. My other point with that is that when you start 3-4 exams is up to you. You don't want to start them too early, because if you haven't done all the content, there's no point. And there's no point you rushing through the content to be able to do exams earlier, but then not learning it well. So don't start them too early such that you don't have all the content. I would suggest starting them maybe when you start food chem, or when you maybe a week into food chem. So maybe that's halfway through Term 3, nearing the end of, like, 2/3 of the way through Term 3. That's probably when you'll be partway through food chem, or you've started food chem. I'd say that's when you can start, because food chem, as I said, 6-7 marks. If you just lose those marks and you just do those ones later, cool, not the end of the world. But I think that's probably the best time to sort of start. Studying for exam, you're studying all year for the exam. You should be revising the content you've been through all the way through the year. You should be going back over fuels once you're doing equilibriums. You should be going over fuels and equilibriums once you start redox. You should be going over all three of those once you start organic. You should be revising all throughout the year. Doesn't necessarily mean you need to be doing practice exams, but you should be revising. I just ticked a question that I didn't mean to tick. I'm so sorry. I don't even know what the question was. If someone asks it quickly and puts it and it comes up, I'll answer it again. I'm so sorry. I did not mean to double click that. Apologies, everyone. All right. Did you get tutoring for chemistry? If so, do you recommend it? I personally did not get tutoring for chemistry. So I'm from Bendigo. I'm sure most of you know where Bendigo is. It's a big town, but there's not a lot of tutoring there. There is tutoring there now. There's actually a significant amount of tutoring there now. But there was not a lot of tutoring back then. So it was not really an option for me. And online tutoring wasn't really a thing because COVID hadn't happened. So there was no real opportunities for me. But tutoring is great. I think now that I'm involved with tutoring as a tutor, I actually find it a lot more useful than what I used to think it was. But you can do year 12 without it. You don't need tutoring to do well in year 12. You can apply yourself, utilize your teachers well enough. However, I do see the benefits of tutoring now that I am a tutor myself. That's one of those things. Any tips for prac experiments? It just depends what you do. I don't really have tips I have tips for specific ones. I can't really answer that question, sorry. I know tips for specific practice ones, experiments, but I don't really have any. I think what's really important about practice experiment, make a mistake, because it's really good to discuss it in the discussion. Say, I made a mistake with my method and it didn't work out perfectly. Thus, I went and discussed it in my your discussion. You have lots to talk about in your discussion. What are your recommended revision study tips? So as I said, I've kind of already discussed this briefly, but essentially what I did was after class, I would revise it, put it down like in a 2-page spread, but it would be like a little notebook type thing, 2-page spread. I'd have all my notes down on there, like my summary of the class and the topic that we just did. I then on the weekend would go and do some practice questions. I had lots of different company exams, older company exams that have like cut up and put into their like each topic, and I'd go through each of those sort of topics. And that's kind of how I went about it. So that was probably my best technique for that there. If you don't mind sharing, what study courses did you get for a 98 ATAR? Great question. I didn't do a UCAT, I did a UMAT because that's how old I am. It used to be a UMAT. I got a 98 UMAT. I don't know what my scores were in the UMAT. They were like out of 200 and something, but I got a 98th percentile. My 98 ATAR, that's a great question. I think I got a 39 in English. I got a 50 in further. I know that's because I tutor it. Great question. 45 in bio and 44 in chem. They were my top 4. And then I had methods and physics. They both, I actually don't remember, but physics was in the 40s and methods was in the high 30s. And they both scaled in the 40s, but they didn't make my top 4 because English had to be one of my top 4. And the other 3 all scaled up, or further didn't scale. Chem scaled up massively and bio scaled up by like 0.5. So that's what my scores were. Yeah, Monash Med's awesome. I enjoy it. So if you're thinking about it, it's worth it. Did you do any extra work during the December, January holidays? I just did sort of like, our teacher gave us a whole bunch of content to do for sort of fuels. So we kind of did all of the rote learning stuff for fuels in Headstart and then in over the holidays. So I kind of did that. I didn't do anything extra beyond that. I went to these lectures, which was extra for me. So if you went to these, then you've already done some extra work. What's an digital resource you recommend for better understanding, understanding? I recommend Ed Unlimited. And I don't mean that as like someone who's working with the business. I mean, it's great. Like the topic, the course notes, they summarize things really well. I've actually worked with the people who wrote the course notes and they're incredible. The course notes are actually really, really good. And I think they will allow you to get your head around really complex things in a very summarized way. I really recommend that. It's the 800 Notes course notes. Handwrite, please do not type class notes. Please do not type class notes. Since I've moved to uni and made a bit of money, I invested in an iPad, which you can see here, and I write my notes on an iPad, but handwrite. Please do not type class notes. Please do not type class notes. You're not going to learn nearly as well when you type class notes. Please handwrite. Please do not. And then I'm so bad at stoichiometry. It's so confusing. Any tips? Biggest tips: do lots of questions. Just do loads and loads and loads of stoichiometry questions. Get chemical equations. Say there's this many grams here. How many moles are over here? There's this mass or this volume of gas. What do I have over here? Just stoichiometry is all just simple maths equations, but the order of it can be really confusing. So the more you do questions, the more you'll get your understanding of the order of things. Stoichiometry is great, and it's in lots of questions. So if you really struggle with it, just do loads and loads of practice questions. That's the best way to get good at stoichiometry. What's the most important topic? Are they all important? I don't think there's one. I think stoichiometry, to be honest, but that's not really a topic. That's like a thing. Yeah, so I've kind of, as I said, I've already discussed how I went about it. This is a very individualized question. I can't really give you the golden answer. So yeah, I essentially did the sort of summarizing, then practice questions on the weekend, and then I constantly just keep going over things. I keep reading over my notes so that I was able to sort of get that information and explaining to people as well. Like if your mates are struggling with a topic that you think you've studied well, try and teach them. It's a great way of sort of learning yourself. No, I did direct entry medicine. If I did biomed, I would only be in second year medicine now because I would have had to have done 3 years of biomed, and I'd be getting old by the time I graduate. No, I did direct entry medicine at Monash. If flashcards aren't useful, what is the best way to revise? As I said, I kind of already discussed this one. And flashcards are still useful. I just don't think they're great for chemistry because chemistry is a lot of discussing things. You're not just putting down a definition. Only fuels has definitions. How did you approach the math sides of chem? I kind of already discussed this with stoichiometry. You just fill out the practice questions, and it's more the maths. The maths in chem. I don't want to sort of be sort of arrogant in this sense, but maths in chem is easy. It is. We all know it is, and we get a calculator. The maths in chemistry is easy. It's knowing when to use what equation that is hard, and that is hard. It's knowing what order to do things in and when to do them. That's what's hard. So the more you do questions, the more you get on top of it. Now I think we're running out of time. I think there's a few questions in here. Yeah, I think questions in there I'll just leave. I don't think they're for, I think the moderator hasn't kicked them through just so they're probably not needed. Easy. All right, there's a few questions here, but I'm probably not going to get to them. I'm really sorry.